Hello. This lesson begins our unit on exponential and logarithmic functions, and specifically today we're going to talk about the exponential function and its inverse. Just before we get into that, I'm going to remind you that in grade 11 you most likely or definitely should have learned a little bit about exponential functions and what they look like. They're the ones that kind of usually start off small and go up, or start off large and get small, whichever. But you should have covered those. If you covered logarithms, fantastic. If not, we're going to start that one from scratch. It's one of those things in the grade 11 course that technically isn't there, but most people put it there because it makes complete sense to talk about it. And if you're unfamiliar with them, that's okay. We're going to do them now, and you'll see why it makes complete sense to talk about logarithms when we're trying to solve exponential problems. So let's jump over to the lesson. And we're going to start off by trying to find the equations of some exponential functions in the form of f of x equals a times b to the x. And we're going to do that from a couple of tables of values. And something I do want to point out is that for most people, as soon as you look at a table of values right now and you're trying to find equations, the first thing that comes to people's minds is how do I do this? And the answer is usually, oh yeah, I take first differences. We do not want first differences for these. We want something called first ratios. We don't want to know what we add or subtract each time. We want to know what we're going to multiply or divide by each time. Technically, it's always multiply. It's just sometimes we multiply by a fraction, which looks like divide. So the table on the left I've set up with numbers that are easy enough that I think we can do it without too much thought. To get from 4 to 12, I have to multiply by 3. To get from 12 to 36, I multiply by 3. And in all of these cases, you're going to see I multiply by 3. Now, if that's not obvious, the numbers were not obvious to you, then you can always do the second value minus the first, the third value minus the divided by, second value divided by the first. So 12 divided by 4, 36 divided by 12, 108 divided by 36, and then you'll get those threes out. Okay, so now if we want our equation in the form of f of x equals a times b to the x, a is just our coefficient that's going to give us a little vertical stretch or compression. B is going to be our base, the thing that we're going to multiply by each time, and that's about it. I will point out that exponential functions can have a plus or minus at the end, so it can be translated up and down, much like any other function can be with our transformations. However, the values of k and the thing that slides it left to right, um, I forget which variable, sometimes we use d, sometimes we use h. I believe we use d most of the time. But either way, the thing that slides it side to side and the thing that compresses it side to side, both of those are irrelevant. And we'll see a little bit more about that later. But basically, they can be incorporated by just changing the values of a and b. So anyway, we're going to start off with a times b to the x. And we already know a little bit about that. We know that the b is going to be 3. That's the thing we're multiplying each time x gets one larger. Now for a, I want to point out that b to the exponent 0 is 1. So if I take a look at what my value is for f at x equals 0, that's actually going to be my a value. Because this would be f at x equals 4 times 3 to the 0, or f at x equals 4 times 1 when x is 0. And that's it. That's how easy it is to find an equation of an exponential given a table of values. Now, of course, we have to make it just a little wee bit trickier, and I can't do much with that other than make the numbers a little crappier, which I'm going to do in the second part here. And so what we want to do is find out what the ratios are here. And remember, we're dividing the second number from the first, so 466.27 divided by 171.53, and we get 2.718. I think we actually get 2.7183, but we'll take that. And if we, actually, you know what? Because these are all rounded a little bit, I'm going to just round off my result a bit. And I think if you do all of these, and you're welcome to, by the way, but I'm going to skip them, you're going to get 2.718 for all of them. So there's my common ratio, or my first ratios. Okay, so now I know that I've got something in the form of f at x equals a times b, which is 2.718, to the x. And unfortunately here, I don't have an x equals 0 value to read off. But what I do have is that when x is 4, f at x is 171.53. And I'll point out that this would work if you chose any of the values in that table, but I'll choose the first one. F at x equals 171.53, a times 2.718 to the exponent 4. So I just plugged in my x and my y essentially. Now in my calculator, I'm going to plug in 2.718 to the exponent 4, and I get out, what do we got, 54.576-ish. And when I divide both sides by that 54 point something, I should get a number just over 3, I believe. And yeah, I get a equals 3.14 something. So now I can conclude that my function f at x equals 3.14 times 2.718 to the exponent x. That wasn't too bad. For those of you who recognize one or both of those numbers in there, I'm going to point this out, and you by no means should recognize this at this point. I'm just going to tell you where I got those actual numbers from. This is actually f at x equals pi, chosen just because I thought it would be neat to use a number that was non-repeating decimal. And the base is actually Euler's number, which is e to the x. So that's the kind of thing you might see in calculus a little bit more, where you'll really focus on the e and the importance of e. And pi, you already know lots about the importance of pi. So I just thought I'd point that out, that that's how that table of values was actually generated. I didn't just choose random numbers. I did f at x equals pi times e to the x. And we were able to get it, at least as a decimal, fairly easily. Okay, let's take a look at a couple of graphs of exponential functions and see if we can figure out what the equations are just from the graphs. And similarly, I think you're going to notice that it's actually pretty easy to do. One thing we really have to focus on is our y-intercepts. And the reason for that is our y-intercept is what happens when x equals 0, which means we have f at x equals a times anything to the 0, which is a times 1, which is a. So right off the bat, for both of these, I can say f at x equals a times b to the x. In this case 2. And on this one over here, it's not as pretty. I'm going to kind of do both these at the same time, just to show you the skill. It's not as pretty, but it's 1.322 b to the x. So now the trick is to find out what b is. Okay, so we started at 2. How do we figure out b from here? Well, we got a couple of options, and one of those options is to plug in any value for x and its corresponding value for f at x by choosing any other point on the graph, which we can do. I am going to show you, however, that it's usually a little easier to pick the value at 1. And that looks like it has a value of 3. And the reason I said that is because if we go from 0 to 1, so we go from here to here, we should multiply by exactly b, because we're going from b to the 0 to b to the 1, which is obviously b larger. Well, if multiplying by b took us from 2 to 3, I think what we multiplied by was 3/2. So now I can say that f at x equals 2 times 3 halves to the x. And that's it. But of course, if the numbers are a little bit trickier to deal with, sometimes that's difficult. So for instance, this number here, a little bit hard to read, at least accurately. So I could go back to the other thing. That number's hard to read. But this number up here is very clearly stated for us. So what I'm going to do is just plug those values into my f at x and x for my equation. F at x is really the y, so that's going to be 7.15. And by the way, for those who remember anything about exponentials, I think you can look at the second graph there and see that it's going to be a value less than 1. It's still going to be a positive b, but it's going to be less than 1, which is causing exponential decay. So I'm expecting a value less than 1, and this will be b to the negative 2. Okay, now I'm going to take both sides and divide by 1.322. By the way, this is not the only way you could do it. If you see a different way and you want to try it, you're welcome to, but I'm going to do 7.15 divided by 1.332, and that gives me 5.3678. So here's a little trick now. I'm going to take both sides to the exponent negative 1, or better yet, I can take both sides to the exponent negative 1/2. Because when I do that, on the right-hand side, b to the negative 2 to the exponent negative 1/2, our exponent rules say multiply exponents. Negative 2 times negative 1/2 is 1, so that side just becomes b. And on the other side, I can just use my calculator for this. 5.3678 to the exponent 0.5 negative. You may have to use brackets to do the 1/2, or if it's a more complex fraction, I just put in 0.5. And I got out b equals 0.4316. Okay, so even though it was a little bit longer, I can now conclude, and I'm running out of room to write, so I'm just going to put up here, right on the graph, f at x equals 1.322 times 0.4316 to the x. Okay, so that was a little bit more difficult, but it's still really just a matter of where does it cross the axis, plug in a point, solve for b. Or alternatively, if we ever have a b value, we can plug in a point and solve for a. That's the nice thing about having an equation that really only has two variables that need to be solved. F at x and x don't technically need to be solved. They are the relationship. So because of this, because almost every exponential function, except for the ones shifted up or down a little, can be solved by or represented by a times b to the x. It's really only two variables, so they become pretty easy to work with. Now we're going to just take a quick look at graphing a function and its inverse. So we'll start off with graphing f at x equals 3 times 2 to the x. Now, you could do this in Desmos, you could do this by applying transformations or etc. I'm just going to do this one straight up by kind of plugging in some points. So when I plug in 0 there, in fact, I'm gonna plug in the points, but I'm gonna say them as I'm plugging them in. When I plug in 0, I get 3 times 2 to the 0, which is 3 times 1. When I plug in 1, I'm going to get 3 times 2 is 6. When I plug in 2, I'm going to get 3 times 4, which is 12. When I plug in negative 1, just because at this point I think you'll see that the f at x is already off the graph once we hit 12, so there's no point in going any further. If I plug in a negative 1 there, I get 3 times 2 to the negative 1, which is 3 times a half, which is 3 times a half is 3 halves. And when I plug in -2, I get 3 times 2 to the -2, which is 3 times 1/4, which is 3/4. And I think you can probably see a pattern developing here. In much the same way that we double, we multiply by 2 every time we go up by 1, we can divide by 2 every time we go down by 1. So this will become 3/8, 3/16, and so on. Okay, given that, at 0 we have 3. Start plotting my points here. At 1 we have 6. At 2 we have 12, and then anything higher than that we're going to be off the graph. -1, we're at 3/2. You know what? I'm not even going to refer to my table anymore. I'm going to remind myself that every time I go backwards 1, I'm going to divide by 2, because every time I go forward 1, I multiply by 2. So 3/2, 3/4, 3/8, 3/16, and we're getting extremely close to the graph very quickly. So we actually do have an asymptote there, a horizontal asymptote. And despite how fast it looks like it's going up, there is no vertical asymptote. The x's can keep getting larger, the y just gets larger much faster. Okay, so that's our graph of f at x equals 3 times 2 to the x. Now our inverse function, f to the -1 x. This is a weird notation for those who don't recognize it, but I'm going to point out that, for instance, when you're solving things on your calculator, if you had sine x equals 1/2, what you're actually doing on your calculator when you're trying to solve for x is you're doing the inverse sine function, or in some cases it's a shift button or a second function button. But what you're really doing is sine -1 of each side. And that means that x equals sine -1. Oh, sorry, this should be a half, not an x. Okay, so we've kind of seen notation that looks like this already with trig functions. And all this is saying is basically the inverse function or the backwards version of the function. Now, as it turns out, the inverse function of this is actually pretty easy to deal with. All we do is what is known as a reflection in x equals y. Now, I do want to point out, I'm not saying it's 1 over this. This is definitely not 1 over the original function. It's the inverse of the original function. So the f to the -1 of x is notation, much like the sine one was. It's not saying 1 over. Like, for instance, this right here was not saying 1 over sine of a half. That's not what that says. It's just saying the inverse of sine a half. All right, so when we do this, all we have to do to graph this is literally reverse these. So just exchange our x's and our y values. And when we do that, instead of graphing 0, 3, we're going to graph 3, 0. And instead of 1, 6, we're going to graph 6, 1. And then we're going to graph 2, 12. And likewise, we're going to graph 3/2, -1, 3/4, -2, and so on. And so our graph is going to look like this, trying to make it look asymptotic, more or less succeeding. Okay, so that one there has actually got a vertical asymptote, but will not have a horizontal asymptote. Okay, that's the extent of graphing an inverse function. If we can graph the original, the inverse is just flip the x's and the y's, exchange them for each other. I'm going to graph this in Desmos, but I'm going to hold off for a moment because I want to look at a little bit more first. First of all, is f -1 at x, or the inverse of a function, is it itself a function? The answer is, in this case, it is. It meets the criteria function. It passes the vertical line test. For every x value, there's at most one y value. So in this case, yes. But not always. The function itself has to be obviously a function. The inverse function does not have to be a function. It will be a relation, but not necessarily a function. What is the relationship between x and y for f negative 1 of x? I'm just going to put out here as a reminder, for f at x, we're really saying that y equals 3 times 2 to the x. That was the original equation. For the inverse function, the relationship between x and y is that x equals 3 times 2 to the exponent y. So we're literally just switching x and y. We take our original equation, our original function, swap x and y out, and then we're done. Now, the reason I wrote it this way with f negative 1x colon and then wrote it with the y is because we have to be able to rearrange that equation for y to actually say f negative 1x equals something. And right now, I'm not sure how to rearrange. Well, that's a lie. I know exactly how to rearrange, but we haven't learned how to rearrange. So for now, we're just going to say that that's the relationship. X equals 3 times 2 to the exponent y. And now I think I'm going to pop over to Desmos and graph those to show you the function and its inverse. Okay, so despite the fact it's f at x, I'm actually going to use y. Y equals 3 times 2 to the exponent x. So there's the graph that we got, exactly kind of as we predicted it would be. And now if I want to graph the inverse of that, it's going to be a little tricky to rearrange it at this point, but I can, like I said, just exchange the y for x and the x for y, except that it somehow dropped the exponent. There we go. So there's the graph in red and its inverse in blue. And what you can see is that that's actually a reflection down that line. So this point up here got mirror imaged over to here. And same with every other point. So that's all it is to find an inverse. Exchange the x and the y. So the good news is for graphing them, we never have to actually rearrange anything to express y equals whatever. We can express x equals something as a function of y. Not something we usually do, but for inverses, very helpful. Okay, now that we've looked at that, can we state the domain and range for these functions? Or sorry, I guess, yeah, they both are functions in this case. For the function and its inverse, because its inverse is not always a function. Just to look up here, the domain and range, it looks to me for the original function, x can be anything, and y will have to be positive. So x is the element of real. There is no x that breaks the equation. And y is the element of real such that y is greater than 0. Going back up to the picture for a second, we can see for that our original function in blue, the y is never equal to 0. It's never negative. So that's it. Well, what about the picture of our green function, the inverse? To me, that looks like x has to be greater than 0, and y is going to end up being able to be anything. Pop-ups everywhere. Okay, so x has to be positive. But our y can be anything. Well, I want you to just kind of make a little connection here that we've essentially just swapped domain and range for the two. For the original graph, x-intercept, there was none. It never crossed the x-axis. There is a y-intercept right here, and that's at y equals 3. And then for our inverse function, there's going to be one x-intercept, and it never crosses the y-axis at all. There, I can form words now. Okay, so it's at x equals 3, it's got an x-intercept, and y it has none. And again, this idea of we're really just swapping out the x's and the y stuff. Vertical asymptote, it had none. Horizontal asymptote, it had y equals 0. And yeah, that's good enough. Y equals 0. For our other one, it did have a vertical asymptote at y equals, at x equals 0. And vertical asymptote, it had none. Sorry, horizontal asymptote, it had none. One more time, just the connection between the x's and the y's kind of swapping off their spots. All right, that is it for this topic, but there's some questions to try, and I will see you in the next lesson.